Today, we'll explore the different ways a line can intersect a parabola. A parabola is described by a quadratic function. Let's say y equals ax squared plus bx plus c, and a line is described by a linear function. Say y equals mx plus k. To find the points of intersection, we set the y values equal to each other. This gives us ax squared plus bx plus c equals mx plus k. We can rearrange this equation into the standard quadratic form by moving all terms to one side. Ax squared plus the quantity b minus m times x plus the quantity c minus k equals 0. The number of solutions to this quadratic equation tells us how many times the line and parabola intersect. We use the discriminant, often denoted as d or delta, which is calculated as b squared minus 4ac. In our rearranged equation, a is a, b is b minus m, and c is c minus k. The value of this discriminant determines the number of intersection points. Case 1, 2 points of intersection. This happens when the discriminant is greater than 0, d greater than 0. Algebraically, this means our quadratic equation has two distinct real roots corresponding to the x-coordinates of the two intersection points. Graphically, the line crosses through the parabola at two separate points. Case 2, 1 point of intersection, also called a tangent. This occurs when the discriminant is exactly 0, d equals 0. Algebraically, the quadratic equation has exactly one real root, a repeated root. This root is the x-coordinate of the single point where the line touches the parabola. Graphically, the line just touches the parabola at one point without crossing it. The line is tangent to the parabola. Let's summarize these findings in a table. If the discriminant d is greater than 0, there are two intersection points. If d equals 0, there is one intersection point, and the line is tangent to the parabola. If d is less than 0, there are no intersection points. Let's look at a specific example. Consider the parabola y equals x squared, and the line y equals x plus c. Setting them equal gives x squared equals x plus c, or x squared minus x minus c equals 0. The discriminant for this equation is d equals negative 1 squared minus 4 times 1 times negative c, which simplifies to 1 plus 4c. Now, let's see the three cases based on the value of c. If c is greater than negative 1/4, d is greater than 0, and we have two intersections. For example, if c is 1, the line y equals x plus 1 intersects the parabola twice. If c equals negative 1/4, d is 0, and the line y equals x minus 1/4 is tangent to the parabola. If c is less than negative 1/4, d is less than 0, and there's no intersection. For instance, if c is negative 1, the line y equals x minus 1 does not meet the parabola. In summary, the intersection between a line and a parabola can result in 2 points, 1 tangent point, or no points at all. The discriminant of the resulting quadratic equation is the key algebraic tool to determine which case applies. Welcome! In this video, we'll solve an interesting problem involving a line and a curve. We need to find the values of the parameter m, for which the line y equals mx minus 2 does not touch or cut the curve y equals m plus 1 times x squared plus 8x plus 1. The condition does not touch or cut means that the line and the curve have no points in common. Algebraically, this happens when the system of equations formed by the line and the curve has no real solutions. To find the intersection points, we set the y values equal to each other. So, mx minus 2 equals m plus 1 times x squared plus 8x plus 1. Now, let's rearrange this equation into the standard quadratic form ax squared plus bx plus c equals 0. We move all terms to one side, preferably the right side to keep the x squared term positive if possible. This gives us 0 equals m plus 1 times x squared plus 8 minus m times x plus 1 plus 2, which simplifies to plus 3. This is a quadratic equation in x. For the line and curve not to intersect, this quadratic equation must have no real roots. The number of real roots of a quadratic equation is determined by its discriminant, d, which is calculated as b squared minus 4ac. In our quadratic equation, is m plus 1, b is 8 minus m, and c is 3. Let's substitute these into the discriminate formula. So the discriminate d is 8 minus m squared minus 4 times m plus 1 times 3. Let's expand and simplify this expression for d. 8 minus m squared is 64 minus 16m plus m squared. And minus 4 times 3 times m plus 1 is minus 12 times m plus 1, which is minus 12m minus 12. Combining terms, we get m squared. Minus 16m minus 12m is minus 28m, and 64 minus 12 is plus 52. We need the condition for no real roots, which is d less than 0. So we must solve the inequality m squared minus 28m plus 52 is less than 0. To solve this quadratic inequality, we first find the roots of the corresponding equation, m squared minus 28m plus 52 equals 0. We can use the quadratic formula for m equals negative b plus or minus the square root of b squared minus 4ac, all over 2a. Here, a is 1, b is negative 28, and c is 52. Let's calculate the roots. M equals 28 plus or minus the square root of negative 28 squared is 784, minus 4 times 52 is 208, all divided by 2. This simplifies to 28 plus or minus the square root of 576 divided by 2. The square root of 576 is 24. So m equals 28 plus or minus 24 divided by 2. The two roots are m1 equals 28 minus 24 divided by 2, which is 4 divided by 2 equals 2, and m2 equals 28 plus 24 divided by 2, which is 52 divided by 2 equals 26. We have the roots m equals 2 and m equals 26. The quadratic m squared minus 28m plus 52 is an upward opening parabola. It will be less than 0 negative between its roots. Therefore, the inequality m squared minus 28m plus 52 is less than 0 holds when m is strictly between 2 and 26. So, the final answer is that the line y equals mx minus 2 does not touch or cut the curve y equals m plus 1 times x squared plus 8x plus 1 when m is strictly greater than 2 and strictly less than 26.